Well, hello everyone. Thought I'd do another contest stream. Uh, how's everyone doing? I just got a Fitbit. I got the Fitbit Versa 3. Really, all I wanted was sleep tracking, but I figured if I was gonna like wear something on my wrist all the time, I might as well have all the smart features, whatever those might be. But as far as I can tell, there are no features that are useful except for sleep tracking and heart rate monitoring. So maybe I should have saved the $100 and just got like the Fitbit charge or whatever. But yeah, I've been looking into making apps. I've already made a clock face. Let's see if I can show it to you. It's my same background as I have everywhere. So on any normal device, like a phone or a desktop, you don't need to like make a whole app to change the desktop. But as far as I can tell, if you want to have your own background on like the clock face, the only way to do it is to make your own app, which I guess makes sense. It's not like the screen is big enough that they could have like a file select flow on the app. But yeah, I'm just getting started. I want to make a caffeine logging app because apparently such a thing doesn't exist. I feel like there should be a caffeine logging app. It seems like the kind of thing that people that have Fitbits would care about, but maybe not. But yeah, I feel like once I log all my coffees, I can like do all kinds of interesting things. Like I can see like on days where I drink more coffee, do I sleep worse the next night? Or on nights when I sleep worse, do I drink more coffee the next day? Interesting questions. Or I could also monitor how my heart rate changes after my cup of coffee. Does it like spike up right away? Or is there no effect? So it'll be interesting once I get that working. I guess the whole app will literally just be a button that has a coffee icon on it. And then I guess I will propagate the information of when the button is clicked to, I don't know. I don't know if I can change the Fitbit dashboard because like the Fitbit.com will give you like a dashboard that shows your steps. And I feel like to be a useful app, I would have to like expose the coffee data to the dashboard so people can like make graphs, or better yet, I could like make a default graph of what I think people want to know. Yeah, so far all I've done is put my favorite image on the watch. Oh yeah, I also want to make an app that sends me a CSV of my minute to minute heart rate. It's like heinous. This whole Fitbit thing is like the epitome of what I hate about modern computers and modern software. I guess like it's the best sleep slash heart rate monitor that one could get, so I'll just have to live with it. But it seems like the whole device just exists to manipulate you. I think that's actually why people get Fitbits mostly. Mostly people are like, oh, I want to exercise more. Let me get this little thing that I carry around that manipulates me subtly all the time, and maybe that'll make me exercise more. But that's not what I want at all. I just want to like collect some data. I feel like there should be some like toggle that you can click when you set it up that's like, would you like the manipulation? And some people are like, oh yes, that's why I got the Fitbit, so I can brag to my friends out how many steps I have. And other people can be like, actually no, I don't want to be manipulated, but thank you. But yeah, I have to like turn off all these notifications that are on by default. I think I've gotten most of them, but it's highly annoying. I feel like it shouldn't be the default, or there should be some like system-wide no manipulation feature. Yeah. And also they constantly trying to sell this Fitbit Premium thing, which is also heinous. So like if I want to see my heart rate or my average heart rate while I sleep, I need to pay for a premium feature. But somewhere else in the app, I can just see a graph that shows my heart rate like at some pretty high resolution 24/7. So I don't know. It's very strange. But I want to like there's a place you can go to download your data, but it's like very low resolution data. It's just like your daily resting heart rate and peak heart rate, and there's no like before I got it, I thought I could download my data and get like all my data and get like a second by second like just a list of every heartbeat I had for the day. It would be perfect, I think. But you can't do that apparently. But I'm gonna try to make an app that does it, that just like makes a CSV and I don't know, emails it to you or lets you download it from their app. I don't know. But yeah, for now I'm just gonna do Codeforces instead of something useful. I didn't sleep that well last night, and I know because my Fitbit told me. Actually, the Fitbit thought I slept fine, but I didn't, so maybe this was a child purchase. But okay, yeah, let's see how fast we can get this one. Gotta go fast. Written by Tourist, nice. Okay. So we got here. We have a permutation of 1 to n, odd length, and we have the following algorithm that sorts it in increasing order. So fi takes an argument, and if it's out of order, then it exchanges them. Otherwise, it doesn't. And then the algorithm does a number of steps. So I goes from along the odd integers, so from 1, 3, so on. Okay, so if I is odd, it calls f1, f3 to fn minus 2, and if I is even, oh, interesting. Wait, okay, less than 999 because it's odd. I was like, why is it not less than 1,000? Okay, so I think the total number of steps will also be less than n. So I think the best way to do this is probably just simulation. We just like perform the algorithm and see when we're done. On the ith iteration, the algorithm does the following. Okay. Yeah, I think we should just simulate this. Okay. So I'll just write f. And so f will take in I and the array, and I'll just sort it. So a at I equals the minimum. Oh, I guess I need a temp variable. Whatever. I'll just say if a at I is greater than a at I plus 1, then I'll just switch them. Then t equals a at I. I feel like there's a better way to do this. A at I equals a at I plus 1. I wonder if I'm missing a better algorithm than simulation, because it seems like a relatively hard first problem if it's the fastest way. So maybe I'm missing something. Okay, and I just won't return anything. I just changed a. Okay. Do I need to? Okay, it's already integers. Okay. Oh yeah, and don't copy my code. Someone did it again last time. I'm gonna get banned eventually. Don't let me get banned. Okay. And maybe I'll just define an is increasing. Def is in. So for I in range, length a minus 1. If a at I is in fact greater than, if it's in fact greater than the next one, then I'm going to return false. It's not increasing. Otherwise, I'm going to return true. Okay, so I got my 2 helpers. And now what do I want to do? I just want to kind of simulate the algorithm. Okay, so for I in range, so I guess I should start at 1. And okay, so for I in range, and it definitely will take less than n steps, I believe. Oh, I think I need to read in n, right? Yeah. Yeah. So for I in range n plus 1 to be safe, who knows? Really, I could just like say while it's not sorted. Actually, that's what I should do instead of having a for loop. So no, I need to keep track of. No, yeah, let's just have a while loop. So while not is increasing, a line, I guess. And let me just keep track of what step I'm on. Step equals 1. So if step is odd, what do I do? If it's odd, I start from the first index. So yeah. So for I in range, so I should start at 0 in this case, and I should go up until n, and I should take a step size of size 2. I wonder if instead of simulating, I should just like compute which index has to move the furthest, and that'll just be my answer, but whatever, I'll just simulate it. Yeah, so I will go up to n minus 2 in this case, yeah, like it should. And what do? I just call f line I. And then I just do the other one, so else, and then I just have kind of the same thing, but instead of starting at 0, I start at 1. And then what do I print out? I guess step minus 1. Oh yeah, I really do have a Fitbit. I'm keeping track of my steps now. Oh yeah, let's test that out. List index out of range. Okay, so I'm calling this on something slightly too big. Oh, I think this should be like -1. Maybe this should also be -1. Infinite loop. So is it always increasing? So while not is increasing, so eventually So it's doing the thing, right? Is it sorting? So if AI, so if it's not in order, that's what it's supposed to do, right? If it's not in order, then it swaps them. If AI is greater than, yeah, then they're exchanged, otherwise it doesn't change. Okay, so if AI, it'll just print the line out at every step just to get a sense of what it's doing. Oh yeah, then I need to kill right away. So it seems to be not changing the order, but why not? Why not? Oh, I'm never increasing step. Huh. I need that. Step plus equals 1. Okay, now it seems to be doing something, and it's getting the right answer. Nice. Let's get rid of some of these print statements. 350. Okay, so I'm pretty confident this is correct because I think it just does the thing. And I'm also pretty confident it should be efficient enough because, yeah, so the total won't exceed 1,000, and I think at most 1,000 steps of the simulation will be required, so we should be able to do quadratic in 1,000. So let's submit. And yeah, I got rid of printing. Yeah, 740A. Yeah, and please don't copy my solution. They'll like ban us both. I wrote it in a comment at the top. I probably shouldn't be streaming it at all, but okay, looks like it worked. Okay, so that was sort of a relatively hard first problem, or maybe not. I guess we're just relatively slow because 1,000 people beat us. But only one person's really ahead of us, so let's just keep moving. See what's up. Okay, so Alice and Boris, not Bob. Okay, they're playing tennis. Oh my God! Last night I played the Super Nintendo Entertainment System tennis game, and it was a delight. Oh my God, it was like one of the funnest gaming experiences I've ever had. It was like Pong ++. Highly recommend. If you have a Switch, you can just download I think it's every SNES game ever, which I guess altogether is less data than a single Switch game. But they're a lot of fun. Okay, so players serve in turns. After a game where Alice is serving follows a game where Boris is serving and vice versa. Yep. That's how tennis works. Each game ends with a victory for one of the players. If a game is won by the serving player, it's said that this player holds serve. If a game is won by the receiving player, it's said that this player breaks serve. It is known that Alice won A games and Boris won B games during the match. It is unknown who served first and who won which games. Find all values of K such that exactly K breaks could happen during the match between Alice and Boris in total. Okay, wait, so what do we get? We get A and B. Okay, so they're playing potentially quite a long match of tennis. The number of games... Okay, so each test case is like one match, and I'm told how many games Alice and Bob win. And I want to find out which... Okay, and... So Alice always starts, so if the sum is odd, then that means that Alice served one more time than Bob, and vice versa. What do I print out? 2 lines. The number of values K such that exactly K breaks could happen during the match, and then in the second line print M distinct integers, the sought values of K in increasing order. Okay. Interesting. And I want to know, okay, for both Alice and Bob, how many breaks could happen? Okay. So I guess 0 is only possible if A equals B plus 1. That's my first observation. Let's see, okay, I guess input is a little different. Instead of line, I'll get AB. Okay. So let's just do some quick math. Okay, so we've got A, B, and let's let N equal the sum, just the total number of games they played. So yeah, so what? So I guess I'll first figure out what the smallest possible number of breaks is. So if A equals B plus 1, then I'll say big B for breaks. So B equals 0 is possible. And then 2, 4. So these are all possible so 0 is possible when A just wins, Alice wins all hers, Bob wins all hers. But then to increase Alice's number of breaks, Alice has to win one of the ones Bob served, but then B has to stay the same. So he has to win one that Alice served, so it has to increase by 2. And it'll increase, every one of these increases by 2 will be possible until we get to 2 times the minimum of A and B. So this corresponds to literally all of Alice's or Bob's wins being breaks. But this is the case A equals B plus 1. So yeah, okay. I guess this problem is like not algorithmically hard. It's just like kind of finicky to make sure you get it right. But then let's say A equals B plus K. Then what's the smallest B? It should be like B equals... so let's say Alice wins every time she serves, and then she wins K other times, and then Bob wins no times. So I guess there's a difference between whether n is even or odd. So I think so b equals k is smallest possible. If n is odd, or if n is even. Otherwise, k minus 1 is smallest possible. And then similarly, it should go b plus 2, b plus k, dot, dot, dot. And then as I set it up, b is smaller than a. Same for this one, I guess. But it should go up, or, sorry, this is a 4. What the heck? And I guess it should go up to b, so I guess the largest that should be possible is when Bob only wins when he didn't serve. And then it should be. Well, maybe it's easier to think about what the largest value is and not what it is in terms of the smallest value. I think in this case it should be everything Bob serves as a break serve, and then everything Bob wins is a break serve, and then Alice can only break as many times as possible, which is every time she didn't serve, which is n over 2, but rounded up. Yes, I think this should be right for that case. And then, yeah, I guess I'm sort of just writing out all the cases. Maybe I should write it in code instead of on the whiteboard. But then let's say we have the other relationship that so this is a equals b plus k, and then let's say b equals a plus k. Oh, and does this hold for k equals 0? So if k equals 0, then of course n is even because a equals b, and then we'll have 0 as possible, which is of course true, and then the largest possible value is n, where everything is a break serve. But that's also possible where they just happen to always break. Okay, so this actually works for k equals 0. Okay. And then here, what do we have? We have so if n is even, we can just reuse this. But if n is not even, then I think b equals k plus 1 is smallest possible. So that corresponds to b winning every time they serve, which is, but then they also have to win an additional k times when they don't serve, and yeah, they have to win k plus 1 times when they don't serve, because b is like half rounded down in the case when it's odd, because Alice always starts serving, right? Alice always starts, right? That's not like an input. Each player. Oh wait, is it not given that Alice? Alice. Wait, so after a game where Alice is serving follows a game where Boris is serving and vice versa. Oh, it is unknown who served first. Oh, okay. This is actually a symmetric problem. Okay. Okay. So in the even case, this is holds, but then in the odd case, things get actually more complicated than even what's written here, but it's complicated in like a symmetric way. Yeah. So I think k minus 1 is small as possible in either case, and I guess it should go up not by 2 but by 1 maybe in the odd case, because it's possible that either player served. So if Alice started, then k minus 1 is small as possible. If Bob started, then I think just k is small as possible. And then what's the largest possible? That's where the player with fewer broke every time, or the player with fewer broke every time, and the player with more so yeah, this is the player with fewer, they broke every time, and the player with more broke all but, oh yeah, it shouldn't be B, right? It should be N minus B. It should be K. A should have broke all K of these. Or no, I guess Alice, we can think about it the other way around, where Alice breaks every time she has an opportunity to, and then Bob's breaks all of in the other one too. So Alice can only break at most half, and then Bob can break all of his. Okay, so I think we can just let this be the minimum of A and B plus half rounded up. That's the most possible. Yeah, so this is the most possible, and it's always possible. And then the smallest possible is just the difference between them. The difference between them exactly if it's even, otherwise the difference between them minus 1. Let's code it up. Okay, so I'll just define k. So k should be, or I'll define n and k. So n equals a plus b, and k equals n minus the minimum of a, b. So if n is even, then smallest should equal just k. Yeah, because whoever won more than half has to break at least k. And then the largest, I think if it's odd, then the smallest should be k minus 1. And then the largest, I think, should be the same either way. So the largest should be the minimum of A and B plus half rounded up. And then I want to, okay, so then if, do this first. So then I should print out the total number that is correct. So if n is even, then the number of breaks must also be even, because they'll always serve an equal number, and there's like an exchange. So So, and what else do I know if n is even? If n is even, then let's see. I believe the answer should be I'll just make a range. So it starts at k, or it starts at smallest, it goes to largest, it takes a step size of 2, it includes the largest, and then I'll just print the length of answer, and then I'll print the join of answer. And then in the odd case, it's just the same thing, except now my step size should be 1. Okay, I'll be pretty happy if this is actually correct. It seems like there's a lot of edge cases. I wonder how comprehensive the testing is. Yeah, I wonder if we should make our own test cases. Okay. Oh, I hate this. I hate this. Int I for I. It's so dumb. Just be smarter. Python really needs to do all my thinking for me, not just most of it. Expected stir instance int found. How could that be? Turns it into an int, does it not? Wait, did I forget to? I think I deleted something I shouldn't have. Oh yeah, so this one should now not be a step size of 2, but a step size of 1. And I still need to print out the length of the answer. But could that be the problem? Or it seems like... Okay, wait. Let me think about what the actual problem is. What the heck? Would I delete that? Should be... Oh, wait, I want to turn it into a stir, right? Did the opposite of what I was supposed to do. Okay. So first it thinks 3 are possible and prints 1, 2, 3. It thinks 1 is possible and prints 1. It thinks 0 possible, it prints 0. Oh, and I guess... Is 0 ever possible? 0 should never be possible, so I don't have to worry about printing empty things here. Like 0 answers should never be possible, but 0 breaks should be possible. Or can A and B be 0? Oh yes, A and B. Oh, but A plus B must be strictly greater than 0. I didn't even think about that edge case. Okay, so let's figure out what's going wrong. So 2, 1. So what's possible? So 2 plus 1 is odd, so it should be in this branch. This k is the sum 3 minus the min. Oh, that's not what I mean by k. It should be max AB minus min. Okay, so now it's working on the first test case. Nice. 4, 0, 1, 2, 3. And now 2, 0, 2 also works. But this one is wrong. So what's this one? 0 and 5. Okay. So I see that we don't actually know whether Alice or Bob is serving, and that changes our answer between 2 and 3. But for whatever reason, they think, or my code thinks that actually there will be no break serves. So that's obviously wrong. Okay, so I guess I'll think about the odd case, but I should make up a test case for the even case to see if it works for that. So what is the smallest? So the minimum of A and B is of course 0. Or, sorry, the max is 5, the min is 0, so k is 5. Okay, so why did I think the smallest answer was k minus 1? Yeah, shouldn't the smallest be like... why does k even play into it? The smallest should be like what happens when the person who wins more, or the person who loses more never breaks. So if the person who loses more never breaks, then the number of breaks... If the person who loses more never breaks. So if you lose more and you never break, then the number of breaks should be the number of wins the winner has over replacement. So in the odd case, this is minimized if that player serves, so they'll serve one more time. So the smallest is if they break the smallest number of possible, which should be the max of AB minus half and plus 1, round it up. Okay, so I didn't break that, and now it's correct there. Okay, but now I'm suspicious about the even case, so let's do one analogous to that one, because I never tested that now. So let's say A wins them all, and it's even. What happens? Oh, yeah, so it's wrong here. Yeah, it's wrong here. So I should just directly compute the smallest. The smallest isn't K, it's... So in this case, the person who serves more... Yeah, so the smallest is if the person who serves more breaks the minimum number of possible, which is just dividing by, and now I can just divide by 2 because we're in the even case. So it still works for the given test cases, and let me test mine, see if it fixed it. 3, yeah, so yeah, there's only one case in an even case where someone wins every one, they just have to break that one. Okay. I think this might be correct now, but I'm getting like a, I don't know, it's not like, I feel like it wasn't like the clearest thinking led to this code. So now like K is actually irrelevant. Yeah, so I shouldn't have thought about it in terms of K. I should have just broke it down into cases right away and just done the computation. So there's no K. I don't know. So what about 12, 2? What's that do? Oh. 5, 7, 9. So the minimum is if they break as few as possible, which is, so they serve 7 times, so they have to break at least 5. So, and then this person would break none. And then what if they break one more? Well, that means this person has to break 1, so that's 7. Then they could break even one more than that. And that's 9, but they can't break more than 9 out of 14, because if they broke 11, then suddenly, why couldn't they break 11? Oh, well, because they actually just serve. Yes, this person only serves 7 times, so of course they can't break more than 7 times. Yeah, so of course 9 is the max. Okay, I think I'm reasonably confident that this is correct. I guess I'll submit. So yeah, 4, 2, 2. That part's right. Okay. I don't know. It's sort of a hard problem to be that confident about. It does seem like there's a lot of edge cases, and okay, cool. I don't know if that should have taken 35 minutes. That's actually kind of slow for a problem such as that. But okay, somehow I guess this problem is actually much harder than this problem because I guess we gained a little bit. We were like the 1000th here, now we're the 600th. But not too happy about our speed. So let's try to pick up the pace. Let's do C, deep down below. In a certain video game, the player controls a hero characterized by a single integer value power. Nice, my kind of game. So the hero will have to beat monsters that are also characterized by a single integer value armor. So on the current level, we're facing n caves. To pass the level, the hero must enter all the caves in some order, each cave exactly once, and exit every cave safely and sound. Safe and sound. When the hero enters cave I, he will fight Ki monsters in a row. First a monster with armor AI1, then AI2, and so far. The hero can beat a monster if and only if the hero's power is strictly greater than the monster's armor. If you can't beat it, you lose. Note that once a hero enters a cave, you can't exit. Each time the hero beats a monster, the hero's power increases by 1. Find the smallest possible power the hero must start the level with to be able to enter all the caves in some order and beat all the monsters. And every time we beat a monster, our power beats 1. Not every time we exit a cave. So does it matter that there are caves at all? Wait, so we have t test cases, then n number of caves. The ith contains an integer ki, the number of monsters followed by ki integers. The armor levels of the monsters in this cave in the order they have to fight them. Okay. So in this case, there's 2 caves, and there's one like 10, 15, 8, and then 12, 11. Okay, so I guess it does matter that there are caves, because the caves determine the order you have to fight the monster. So no matter what power level you had when you entered this cave, you'll leave it with power level +3 if you survive. Okay, so in this case, 13 is optimal, because you can come into here, and then you'll leave with 15. We need strictly greater, I guess? Yeah. So we can't enter with 12 because we die, so we need 13. Okay, and then the caves can be quite large. And then the number of caves can also be quite large. So we need something linear in the total number of monsters, I guess. So maybe we should start by thinking about one cave. So if there's one cave, so say you have one cave, K1 up to Ki, what power do you need to pass it? Okay. So you need, so I guess we can go over it and keep track of what you need. So what do you need at step J? So it starts at 0, and then so you need the maximum of what I wish I call it like previous need. So I'll say need starts at 0, and then need should now equal the maximum of what you previously needed, plus you need to defeat this guy. You need to defeat KJ, but you'll have more than you started with, so yeah, you need kj, but you actually don't need kj. You need kj minus j minus 1. Right, so like if we have some sequence 5, 7, 3, then like I guess you need 0, and then I come here and I'm saying, oh, actually you need 5. So we're at an, I'll say plus 1. Or you need 6, because you need to defeat this monster, but okay, so then you defeat it. So now you have 6. And you get here, and then I'll be like, oh, actually what you really needed was 7. You needed 7, but by the time you got here, you would have already gained 1. So you really only needed 6, but plus 1, because you need to strictly beat it, so 7. More of these want to become famous chats. Thanks, W New York 2844. And I'm going to index from 0, so instead of j minus 1, I'll just say j. So minus j plus 1. So yeah, okay, I can compute this for every cave. So compute what you need for every cave. Okay, and then I think it suffices to go through the caves in the order of least strength needed. Yeah, so if you only need yeah, so if you only need like, so cave 1 needs 5 strength, cave 2 needs 10, cave 3 needs like 12. It can't be necessary to do cave 3 before cave 1, because you can do cave 1 before cave 3, and maybe cave 1 doesn't prepare you for cave 3, but maybe it does. Yeah, so we can just do them in order of least strength required. And then the strength you need at step K will be what you need is what you thought you needed. With maximized with like the need that you need for this cave. So I guess I'll call that need I minus the amount you've gained. So I guess total thought. Okay. So it shouldn't be too hard to code up. Oh, okay. It doesn't seem to like this. Whatever. Ubuntu's broken. Sad. I guess I can't pin it always on top then. Oh, there. Okay. Okay, no, okay, it's working. Okay, so we've got n cases. So we've got teeth cases, and then the first thing we read is n, the number of caves. And then we iterate through that. So So let's say caves is an array, and for I in range n, I'll read in line, and then maybe I'll keep track of the sizes separately. So then what do I want caves at I to equal just the tail of it. So it should be line starting at 1, and I want the size at I to equal the first one, line at 0. Okay, now I've got all the data. And now let's compute the amount of power you need to go through a given cave. So power needed and then for I in range n, for I guess I'll say j in range, I called it sizes at I. So I can just use that variable. So power needed at I should equal the maximum of what I thought I needed, and the size of the monster at this step. So sizes at, or not sizes, caves at I at j minus j plus 1. Okay, and then I think that'll compute the power needed for every cave. Let me just print them out. Yeah, let's test out how this is working. Put it over there for now. Yeah, I found this menu to be very buggy. It's sort of unfortunate. Line, oh, is it line? Yeah, sorry I keep minimizing that. It's like a anti-copying thing. Okay, so what did I guess? So the first cave, you need a power of 43 to get through. That is not right. No, it is right. You need to beat this one monster, so 43, yeah. And then the second one, yeah, you only need a power of 15 because you will be 1 greater by the time you get there. And here you need a power of 13. So it correctly knows how much power you need to defeat a given cave. And now we need to combine all that information. Okay, so let's sort the power needed. Okay, so all I really need is the power needed and the size. So let's zip up the power needed and the size. Okay, so if 2 caves need the same amount of power, it doesn't matter what order you do them in, because if you can defeat one, you'll be able to defeat the other, and they'll both make you equally strong. So I think I can just sort this. I'll just call it data to be as nondescript as possible. It's all the data we need, and now we just go over this. So the answer can equal 0, and then for I in range n. It's sort of the same algorithm. The answer should equal the maximum of the answer I thought I needed and the power needed at this step. So power needed to defeat I minus the total growth I've experienced. I'll just call total. Beginning total is 0, and then at each step total should just increase by the size. Oh, so data at I for the strength needed, and then data at I for the growth experienced. Size is not defined. 43, 13. I think those are the right answers. This is definitely not a very comprehensive test, but I think it's the correct algorithm, so I guess I'll just submit. I don't know if I should make some of my own test cases that require more. Yeah, so you need 13 to get through here, and then once you have 13, you'll have 15, so you'll be able to get through there. Yeah, and I go in order from this one to this one because this one requires one more. It all just makes a lot of sense to me, so I will submit. Nice. Oh, okay. Okay. Oh, we fell behind. We were like 600th here, and now we're like 900th. Okay. I guess this problem was not that hard. I had some time talking and thinking. Okay, so D has 2 parts, then we have E and F. Looks like D1 is not too hard, but D2 is a lot harder. Let's see what we got. Okay, so this version of the problem differs only on the constraint on N. Note that the memory limit in this problem is lower than in others. Oh, okay, so we have a limit on memory. That's sort of unusual. Okay, so I have a vertical strip with n cells numbered from 1 to n, top to bottom. And then here n is 10 to the 5th, already quite big. Oh, that's already like so big that mostly linear algorithms will be necessary. I wonder if it's even possible to do the next one in Python. I guess we'll see. Okay, so we have a vertical strip from 1 to n. I also have a token that's initially on the top at n, and I will move the token up from 1 to n. 1 to n top to bottom. Okay. And then I'll wait. 1 to n top to bottom. Oh yeah, so I start at n, I go to 1 going up. Okay. So let the token be in cell x greater than 1 at some point. One shift of the token can have either the following kinds: subtraction or floored division. So I can choose an integer y between 1 and where I'm at, inclusive, so I could choose 1 or the next one. And I move the token from cell x to cell x minus y. Okay, so I could, I always have the option to just move all the way to the end. I can move anywhere, okay. Or I can choose an integer z between 2 and x inclusive and move it from x to cell x over z. Find the number of ways to move the token. Okay. So it's a count problem, not a fastest possible solution problem, because there's 2 ways to get all the way to the end. So find the number of ways to move the token from cell n to cell 1 using 1 or more shifts and print it modulo m. Okay, yeah, because I guess it'll be quite large. Okay, so they'll give us m, but they guarantee it's a prime number. That's sort of interesting. I wonder why they do it that way. Usually they just specify like 1,000,000,007 or 100,000,000 or 7. I forget. Note if there are several ways to move the token from one cell to another in one shift, all these ways are considered distinct. Okay, yeah, that makes sense, because if there's always 2 ways to go to the end, you can always go to the end by just going to the end, subtraction by x minus 1, or you can go to the end by dividing by x. So there's always two ways to go to the end from any cell. Okay, so print the number of ways to move the token from cell n to cell 1 modulo m. Okay, so I'm guessing in the next one this is like going to be 10 to the 9th, and I'm going to have to be like much smarter, but I think I know how to do this next one. So let's just read the bound of the next one so we can think about whether it makes sense to do them at the same time. Oh, 10 to the 6. Interesting. So we can just do a linear time algorithm in both. Oh, and the nice thing about it is it'll be very easy to come up with test cases. The input and output are quite small, so I think we should be able to do this in Python. So there's sort of like a DP approach. Okay, this is actually more complicated than I realized. I thought we could just like start at n and then like put weight on everywhere that follows. But maybe it's more complicated than that. Okay. Yeah, this is sort of an interesting problem because I guess this floor division is actually very collision-y. So like there's lots of ways to go to 2, and then there's like fewer ways to go to 3 and fewer ways to go to 4. And then there's no way to get anywhere in between like x over 2 and interesting problem. Oh, I can move it around, but I can't get rid of it. So yeah, to work. Doesn't want to go away. Okay. So we start at n. So from n, there's one way to go to 1 ... n minus 1. But I can't waste time filling these in. I can't like keep an array that's like number of ways to get to k, because then it would be like quadratic in n, which is obviously not acceptable. But I think I'll just keep track of the number of ways to get to k. So So there's actually not that many division steps. So yeah, I guess I should handle division and subtraction slightly differently. So I'm thinking we go from n to 1 and then do all the divisions. Computing, so our goal is to compute number of ways to get to k. And then so we can compute number of ways to get to k and number of ways to get to all of the above. So then when we do this, like when we do to this step, like the subtraction step, any way we could have gotten to something above has a way to get to where we are now by just direct subtraction. And then we also have to handle division. So at each step, we can just do all the divisions. So I'm doing all the divisions. So if we're at k, we want to compute so the number of ways to divide to 1, 2, 3, ... Yeah. And we floor this, right? So we up to k over 2 floor, and then k, because we can get to k by dividing by 1. Wait a minute, can we just stay where we are? Oh, we're not allowed to stay where we are. We have to divide by something strictly greater than 1. Yeah. Can't have loops. We have to strictly decrease. Otherwise, it'd be infinite. So k over 2 is the largest integer we can get to, and we can get to it by dividing by 2. Okay. So let's see, number of ways to get to 1. So this should equal, so we can get to 1 if we divide by anything greater than k over 2. So it should equal the size of the set k over 2 rounded up. Yeah, so if it's odd, we can just, yeah. So we have to round up. And every integer up to k will get us there. And then the number of ways to get to 2 . So this should equal the size of the set. Okay, so like I guess k rounded down, k minus 1 over 2. And then up to k divided by 3, but rounded up. Wait, I guess strictly rounded up, right? So if so what happens if k is odd? If k is 3 divided by 2, yeah, equals 1. Okay. Right. And so I think the general formula will be the number of ways to get to I should be the size of the set, like the previous, so divided by I, but rounded down, because if it is divisible by I, then you'd get, oh, do I want to round down? I guess not. If it's even, I want to like exactly k over 2. Yeah, because if k is even, then if I divide by 1/2 of it, I get 2. But if it's odd, then I'll round down. Yeah. So same for I. So up to k over I. And then down to the previous thing. Oh yeah, and I guess this should just be like k plus 1. Not k plus 2. Yeah. No, I want to round up. If k is divisible, maybe I should just add 3 even. So if k is divisible by 3, it should be in the next set, because you'll get 3 by having 1/3 of it. And then here I want something. So if it's, yeah, so plus 2, and then, so I down to k plus, so down to I plus 1, k plus I. So the cardinality of these sets. Okay, so I can't just go through and compute all of these because I can't go all the way up to k over 2. That'd be too much. But most of these should be empty. Right? Yeah, so there should be lots of ways to get 1, lots of ways to get 2, lots of ways to get I. But eventually we're going to have that eventually we're going to have k plus I over I plus 1 is greater than k over I. And then when that happens, we'll have no solution. So when will this happen? So let's just multiply through. We'll have I times k plus I greater than k times I plus 1. This is ik plus I squared, ik plus k. So ik's cancel, so an I squared is greater than k. It should be empty. So we only have to go up to the square root of k. Okay. Why does that make sense though? Shouldn't like there be some sparse solutions? Yeah, I feel like this should depend on the rounding. I guess this makes sense. Maybe we need to like. Okay, I guess we just go through these until. Yeah, we just go through these until like the sets start being empty or size 1, and then the only way to get to like an integer I is to like have an explicit divisor, because they'll be too spread out. Like when I is very large, the only thanks Hubzada, thanks for following. Yeah, so eventually they'll be like singleton sets, and then we can just iterate through the divisors of k. So okay, I see why there's like a cutoff around 10 to the 5th, because I kind of want to have like an algorithm that's going to be 3/2 complexity, where like I iterate from n to 1, and each step I do something that's square root of where I'm at complexity. because at each step I'm going to want to find the divisors. Okay. It's a compute. Oh right, I pinned this always on top. Okay. Let's do that. It's D, right? We're on. Okay, so all we read in is N and M. Oh, and I guess they have N and M, so we can't just cache the solution because we couldn't submit numbers that large. So N is the number that we care about, and M is some prime that we're just going to mod by at the end. Okay, so how does this go? So for I in range, so we'll start at N. We're going to go to 1 backwards. And what do we do? Let's keep track of the div ways, so the number of ways we can divide. Oh, right, they said there was a memory limit. $100 megabytes. Okay, I imagine we can have an array of size 10 to the 5th then. Oh yeah, I wonder if this is just around the cutoff. So 10 to the 5th is like 2 to the 15. Or no, it's like it's like 2 to the 8. And a megabyte is a million bytes. Okay, so it seems like we're good. No, it is 2 to the 15. This is like a 2 to the 20. Okay. So it's, I guess, close in the next one when it's like up to 10 to the 6, 4 times 10 to the 6. Okay, so maybe like that's the key, is you just can't like have all that in memory. But for now, I'll just do it this way. So we want to compute the number of ways to divide to get somewhere. Times n. Maybe n plus 1, so I can not worry about off by 1 errors. And then say total ways to get where where we are. So there's one way to start at n, and that's 1. Yes. And then I want to compute the number of ways to jump from n to all these other places. Okay. So for I in range n to 0 minus 1, let's just say so for j in range, so this is, I guess, ways to land somewhere. So 1 up to I minus 1. So I want to compute the number of ways to land at j. Maybe instead of I minus 1, I'll go math.square root I minus 1 square root I. Okay, so I want to compute the total number of ways to land at j. So say the div ways at j should equal the cardinality of those sets I described Where is it? So it should be k integer division I minus k plus I integer division I plus 1 plus 1. And then, so that's the number of ways to land on J on the small side. So on the small side, there's many ways to land there. But then on the large side, there's fewer ways. So let's just see if this does divide us. And then if it does divide us, then that'll give us a large way as well. So if I is divisible by j, then let's say that div ways at j or I over j. I guess it doesn't have to be integer division at this point because it should evenly divide. Should just plus equal 1, because that's exactly one way to get there from dividing it. And then, so this is like a small divisor, so if we changed it by just 1, it would hit something else. And yeah, and if we get above this range, then we'll hit on the other side, I think. Okay. I think this is right. Okay, and then let's say at the beginning, our total ways is plus equal the number of ways we could have landed here by division. And then at the end, we just print the total ways. And actually, we don't have to do anything at 1. I won't include 1. Yeah, so this computes the total ways we could have arrived at any number greater than 2. All of those have a subtraction way to get there, so that's what's counted in total ways. Oh, and then instead of adding this and that, I should multiply it by the total ways we could have gotten where we are. And then I need to mod out by m like everywhere. Just do it at the end. Mod m. I'll put parentheses. Make sure there's no PEMDAS errors. Where's mod and PEMDAS? And I guess this has to be, I don't have to mod out there because I modded out everywhere else. See if this works. Copy. Oh, there's no T. Float object cannot be interpreted as an integer. Oh, I should just floor that, I guess. Wait, I wonder if there's actually a more natural way to do this. Oh yeah, I guess like the natural way is to compare j squared to I. But I'll just int it. One. That's not right. Okay, so this shouldn't really matter. All that matters is this 3. So okay, so what can you do? So we start at 3. So total ways to get to 3 is 1, and then we do all the division. So for j in range, I think I should round up here. Name k not defined. What is k? Oh, k is actually where we are. Wait, this should be n over j, or I over j. Okay. Still thinks it's 1. Okay, so what should happen here? We should start at 1, and then, so the square root of 3 is 1, but we add 1, so 2, so it should check just 1. And then the number of ways to get to 1. So the number of ways to get to 1 should be 3 minus, so this will be 4 over 2. So 3 minus 2 plus 1. So it should be 2. And that's correct. There are 2 ways to get to 1. You can divide by 3, or you can divide by 2. Yes. Oh, I wonder if it should be total ways plus div ways. Yes, it should be. Oh, what did I do? Wait, where'd I go? Oh, all right, there we go. 3. Okay, that's progress. 3 is closer to 5 than 1. Okay, so yeah, I should print out more things for debugging. Let's print out div ways just to see it. So right, so 0 corresponds to 0. It's not meaningful. There's 2 ways to divide to 1. Wait, there shouldn't be 1 way to divide to 2, right? So how could you divide to 2? Like, so you start at 3. So j of 1 is not meaningful. I should get rid of that. J is greater than 1, and what's that? So now there's no way to get to 2, which is correct. So there's only, yeah, but there should be a 3rd way to divide to 2. You should be able to divide to 2 either by dividing 3 by 3, dividing 3 by 2, or dividing 2 by 2. So why is it not getting that one? So it should always check 1, and then, so we're at 2. How many ways can you divide to 1? 2 over 1 is 2, and then 3 over 2 is 1. And total ways. I wonder, I should get rid of this and then mod it out here. Yeah, I'll print out total ways as we go, I guess. So total ways is 1 at the beginning, and then it should also be 1 at 2. Wait, why is the answer 5? Okay, so the only way to get to 2 is just subtracting 1 from 3. So there's one way to get to 2. And then, so from 3, there are 3 ways to get directly. Oh, wait. Okay. I need to keep track of like total above. So total ways and total above. Okay, and then so this is the total ways to get where we currently are. Oh, wait, now I'm confused. So every way you could be above, you can come directly to any other point. Okay. Yeah, because so when you get to 1, the total above should be like 2, because you can be at 3 and go directly to it, or you can be at 2 and go directly to it. Right, so the total ways I could be so what do I want total ways and total above to represent? I want total ways to be the total number of ways I could be at my current location. Okay, so total above so the total ways I get at the current location should be the total above, like all the ways I could be above, plus the number of ways I could have divided directly to where I am. Mod m. So that's the total ways I could get to where I currently am. And then the total above in the future should be equal to the total ways I can get where I am. So I guess it'll be like an inclusive thing, plus the total above. So anyway, I could have been above where I am. I could have come directly here. Yes. Yeah, anyway, I could have been above. I could have come directly here, or yeah. So it's an inclusive thing. And then this should now be total above. All of those lead here. Yes, okay. 8. Now it's too big. Wait, okay. I think I should not include 1. Oh, I'm not including 1. Okay. So there's no, okay, so. So total ways. Total ways is 1. Let me print total above 2. Okay. I guess total above is actually 0 in the beginning. There's one way to get okay, that's not right. Total ways I guess actually I don't need this. I just need this. So when I come to n, there's just one way to get to n. I just need to update the things below me. Total ways is not. Oh yeah. Wait. Oh yeah, I guess I referenced it here. Okay, so there's one way. It's like I can't really make up my mind whether it's inclusive or not inclusive, which is I guess not a good place to be. So why is this so big? There should only be 3 ways to get here by division. Maybe I should, okay, I think this needs to be strictly less than I. Because I don't want to count that twice. No, that didn't fix the bug. It's hard to reason about. So I guess J is sort of like doing 2 things in this loop. It's like the target and this line. So I can hit the values from 1 to the square root of n, and this is the number of ways I might hit them. Hey, this should. Yeah, I guess I should update this in the line above. Sorry, I need to think straight here. myself into contortions. Let's see. I guess I'm not really very clear on what I even want total ways and total above to represent. Like, I want total above to be the total number of ways I could have landed on any square above me. And then I want total ways to be the total number of ways I could have landed exactly where I am. So how many ways can I land exactly where I am? That would be the total number of ways that I could have landed above me, because all of them can come directly to me, plus the number of ways I could have divided to end up where I am. Okay. And then I guess I don't want to update total above until the end. So in the future, so total above should be like inclusive of me. Right, so total ways should be like 1 to get here, 1 to get here, but total above once I get here should be 2. There's like, yeah. And then, but it's not 2. So total above is 1 at this point, and then it increments to 2, and then here So maybe I don't want to increment total above so aggressively. So I print out total above what the so before I even get in, I'm sort of like saying total above is maybe I want to start total above at 0 and then just say like let div ways at n equal 1. So then the total number of ways I can get to the first one is 1. It changed the behavior a little more than I expected. Yeah, that's bad. All right, so right, so there's no ways it's above in the beginning, but then I'm saying in the future there's 1 way above the total number of ways I could have gotten there. So when I go through this first one, no ways above. When I go to this one, there's 1 way above, which makes sense because there's just 1 above. And then when I get here, there should now be 2 ways above, which is correct because, yeah, 4 plus 2. Now I just need to make the rest of it work. So maybe I should print out div ways and see how that's updating, or just put it in here. Okay, so for 3, it's correctly seeing that there's 2 ways to get here. But it's not correctly getting, like, there's 1 division way from 2. So, oh, maybe this, I should get rid of this. No. So for j in range 1, so for 2 it'll be 1 to the square root of 3, 1 to 1. Oh, wait, I guess I should round up outside. I mean, no, that's the right place to round up. So, yeah, square root of 2, rounded up will be 2, so it'll just check 1. That's the only place we could end up. And then, so how many ways can you get to 1 from 2? It should be 2 minus 1, or, yeah, 2 minus 3 over 2, so 2 minus 1 plus 1. Wait, is that right? Maybe then it's not adding anything. How can that be? We are checking 2, right? So we start at n equals 3, then we do n equals 2, and then, yeah, I'll just print out the result of this equation. I can't really reason about it right now. Okay, so it starts out as 2 because there's... Oh. This should not be equals, it should be plus equals. Just like it is here. Now it'll be too big. Yes. Okay, big mistake. So this shouldn't be quite so big. It should be just 1 in this case. So why is it not 1? So what is this? This is I over 2, or this is 2 over 1. The number, this is 2 over 1, which is 2. Okay, I wanted to round up here, I think, but I guess it's not rounding up. I wonder if it should be j plus 1, because then it'd be 2 plus, just want to round up. And so 2 over 3, so 0, but I want to round up, but I guess I want, do I not want the plus 1? I probably do want the plus 1. Look at these equations I wrote down. Were they right? So the number of ways to get to I should be this set. So one way I can get to I is by dividing by k over I. It's the largest number, the height of the set. So to get to 1, I can divide by 2. I can divide 2 by 2. And then it's the smallest way I could get to 2. It should be the same thing. So what would get me to 0? Dividing by or what would get me to the next number, which would be 2. It would be dividing by 1. So oh, should it be like I minus? So this will be a smaller number, so if I divide by it, I'll get a larger number. I wonder if there's some like problem when it's so small as 2. So it works for 3, but it doesn't work for 2. I wonder if it's just like a special case. Yeah, because it's like to get to 2 from 2. Yeah, I wonder if it should only be this like other case and like not even do this thing and just get rid of this if j is greater than one line. Or yeah, so if I get to 2, so so 2 mod 2 is of course 0. Oh, maybe the line is right, but it's sort of like double counted. Because no, we should only do it with 1. It should be this. I wonder if there's like some special case for the last one. So this is should we just like I plus j plus 1 or something? So I is 2, j is 1, so it's like 3 over 2. Yeah, maybe just plus 1. Okay, it worked. I can't have that much confidence in that though. Let's comment these out and try other cases. Let's try this one. Oh, what else am I printing out? I'm printing out too many things. Just don't want this at all anymore. 27? Is it right? 25. Oh, it's so close to right. What would be most valuable to see? Probably the div ways. Okay, so when you start at 5, how many ways can you divide to 1? You can divide by 5, 4, or 3. So that's correct. How many ways can you divide to 2? You can divide by 2. And yeah, okay, that's exactly right. So after the first step, it's right. Now you go to 4. How many ways can you divide to 1? You can divide by 4 or 3. So that's exactly right. How many ways can you divide to 2? Oh, only exactly 2. So this should actually be 2 at this step. Okay, so that's a mistake. Then you get to 3. How many ways can you divide to 1? You can divide by 3 or 2. So this should just be 7, I think. Oh, wait, no. There's I'm not just adding the total ways to divide to it. I have to add by like the total ways I could have gotten above as well. So actually, I think this might be correct as far as I can tell. Yeah, because so this first line is correct, and then the second line. Oh, okay. So there's only one way. Well, there's only one way to get to 4. Okay. Right. Yeah, because total above. Yeah. Let's print out total ways. the total ways to get to 5, just 1. Only one way to get to 4, you can just subtract 1. There's 2 ways to get to 3, because you can subtract from 5 or from 4. But then there's many ways to get to 2. Yeah. Okay. Yeah, I guess this weighting by total ways makes it sort of confusing to tell the diff. I wonder if I should like take that out to help debugging or something. And what other ones does it have? Okay, the next one's of course huge, and I guess this will be hard to evaluate whether it's correct or not. But yeah, let's get 25 working. I feel like if we get 25 working, the code will just be correct. So yeah, let's go through. Okay, so for this one, it's correct, but what about this one? So now you're at 4. There's only one way you could be at 4, and from 4 you can get to 2 precisely by dividing by 2. Okay, so this line then isn't quite correct. So you're at 4. You compute the square root of 4. That's also making me concerned. So you compute the square root of 4 and get 2 plus 1, so that's 3. So you're going to check 1 and 2, which is good because you can get to 1 or 2. Oh, okay. I think there's an issue here. So if j is greater than 1 and it evenly divides it, and we didn't already count it, so we don't have that j times j equals I. Not equal. Because if it does equal I, we'll have already counted it up in this step. So that's why we're double counting it and getting 3 instead of 2. Nice. Let's test the other one. I guess I should mod some things out. Ooh, sad. Well, debugging that is going to be hopeless. Let me mod this out. Hopefully that's the problem. Hopefully. It could be, because I am adding up 2 numbers that... Oh, I do get a different number, but not the correct number still. Oh dear. Yeah, and it can't be a problem with not modding things out enough, because I don't think we could get an overflow with this m. Let's think. I guess I should test more inputs. Let's see what 6 does. Just go one at a time. Just copy and paste this prime. It shouldn't really matter what prime we use. Looks like they use the same prime in all their inputs. 55. Oh, and let's print out some data. Div ways and total of. Ah, heck. Oh. 6. Okay, so we start at 6. So there's 3 ways to get to 1. We can divide by 6, 5, or 4. Then there's 1 way to get to 2. We can divide by 3, and 1 way to get to 3. We can divide by 2. So this first line is correct and good. Then what happens next? So we're next at 5. So there's only 1 way to get to 5. You could have just subtracted from 6. And then from 5, there's 3 ways to get to 1. You can divide by 5, 4, 3, and then 1 way to get to 2. You can divide by 2. So that's correct. Same thing for 6, 5, 4. There's only one way to get to 4. Oh, no. There are now 2 ways to get to 4. Right. You can either subtract from 6 or from 5. So there's 2 ways to get here. And then from 4, there are 2 ways to get to 1. You can divide by 4 or 3, and you multiply by 2 because there's 2 ways to get here. So that weights 4 more ways there, and then there's only 1 way to get to 2. You can divide by 2, so that weights 1 more there. Okay. And now we're at 6, 5, 4, 3. Now we're at 3. I think this might be wrong, because so there shouldn't be 5 ways to get to 3. You can get to 3 by subtracting from 6, 5, or 4, or dividing from 6. So why is this 5 and not 4? Yeah, then this would be 18. Wait, yeah. Why is that the case? So what? So we're at 3. The div ways at 3 should be 1, right? It's printed right there. And then the total above. Yeah, so this is the third step, right? So 6, 5, 4, 3. So it's saying that there's 5 ways to get to 3, but I believe there should just be 4. Why the discrepancy? So total above starts at 0, and then yeah, I should print out total above at each step 2. So it thinks total above for 3 is 4. Yeah, so I think total above 0, 1, 2, 4. Why is that? What is total above? Total above just increments by total. Oh, it's like Fibonacci, but it shouldn't be, right? It should. Huh. I like sort of double counting. So what are the total number of ways to get to a given location? It's all the ways you could divide there, and everything above it that could have just subtracted directly there. And then once I compute the total number of ways to be here, wait, am I doing this too soon or too late? So once I compute the total number of ways to be here, then total above for the future should be the total number of ways to be here plus the previous total above. So total above Oh, no, this is actually just correct. This is just correct. What am I saying? Right, yeah. This is correct because how many ways can you get to 3? You can subtract from 6, you can subtract from 5, you can subtract from 4, or you can just divide straight there. That's 4 ways. But you can also, from 6, go to 5, and then from 5, go directly there. Or you can go subtract from 6 to 4, then go there, or subtract. So it's actually too low, not too high. So yeah, so the number of ways to get to 3. I mean, so is it wrong in other places too? So there's only one way to get to 6. That's correct. And then how many ways to get to 5? Just one as well, because you can subtract directly from 6. But then how many ways to get to 4? There's 2 ways to get to 4. You can subtract directly, or you can go 6 by 4. So and it's getting that correct. It's saying that there's two total ways to get to 4. And then for 3, you can divide. You can come from 6. You can come from 5. Or you can come from 4. And there's 2 ways to come from 4. You can go 6, 4, 3, or 6, 5, 4, 3. Oh no, so it's correct. It's saying 5, and that's the correct answer. Huh. It's almost more troubling because I'm looking for bugs, but I think that's correct. Yeah. So then there's 5 ways. So 1 way to get to 6, 1 way to get to 5, 2 ways to get to 4, 5 ways to get to 3. And then from 3, you can divide by 2 or 3, either way you get to 1, so that's 10 ways. So 10 goes to 20. And now you're at 2. So how many ways to get to 2? There's all the division ways, of which we found 4. And there's also all the step ways. I guess it's getting a little complicated to like compute, but from 4, there's 1 division. So I guess there's so there's apparently 13 ways you can get to 2, and then each of them should contribute 1, so this should become 33. And now in the end, so total above should go from 13 to 22, because there's all the ways you could have gotten to 4 and all the things previously. It's very difficult. So it's right on that one. Right on that one. So if it's right on this, it sort of has to be right on 4. But then it's a lot of output, but doesn't quite agree. Okay, let's try something in between. Let's try 10. It's very hard to understand. So what can you do from 10? You can divide by 10, 9, 8, 7, or 6 to get to 1. You can divide by 5 or 4 to get to 2. You can divide by exactly 3 to get to 3. Oh, you can divide by 4. Or yeah, okay, then you divide by exactly 2 to get to 5. So this is correct on the first line. Okay. Okay. And then how many ways to get to 9? There's just one way to get to 9. And then from 9, you can go to 1 by dividing by 9, 8, 7, 6, or 5. So that's 5 ways. So that becomes 10. You can get to 2 by dividing by 4. So that increases by 1. You can get to 3 by dividing by 3. So that increases by 1. And you can get to 4 by dividing by 2. Wait. Okay, so there's a bug finally. So we can hopefully fix it. Maybe. Huh. Oh yeah, I wonder if this simplification, or like this, is maybe just wrong. So wait, so 4 is above the square root. So in theory, it should appear here. Maybe I shouldn't have this perfect division thing? Wait, so every number... Every number from 2 to the square root of the number should give a different number when I divide by it. They should be spaced out enough. Yeah. Like, so I actually, maybe I just don't want this condition. I'm worried this is gonna change everything. But maybe that's just an incorrect requirement. It doesn't change that. Does change that, so I'll have to check that. Okay, wait. Let's see. So from 6 we can get to 1 by dividing by 6, 5, 4, and then we can get to 3 by dividing by 3, and okay, so it's somehow collapsing two things here. I mean, why would it collapse anything? Oh no, this is 5, not 6. So from 5 we can get to 1 by dividing by 5, 4, 3, and we can get to okay. Okay, so the issue here is that so we're kind of counting both of these in a way that we shouldn't. Yeah, because this should just be 1. And then that 1 is like double counted, so yeah, if we just correctly count it, then it'll be fine. Okay. I guess the problem is when the integer division equals the other value. So if I integer division does not equal j. What? Oh, it's right. Nice. I'll test the other ones, I guess. Wow, I would not describe myself as having a high degree of trust in my code, though. Like, if it's correct up to 42, how could it be wrong, you know? Yeah, I don't think I had the most structured way of thinking about the code I was writing here, but looks like it's correct. Let's test its efficiency. So up to 2 times 10 to the 5th. Wait, so this is 10 to the 0, 1, 2, 3, 4, 5. Okay. And give it the same prime. Oh, take out these prints. One, two, three, four, five. Oh dear, that is a bad sign. Guess it's good that I tested it. I thought this would be fast enough, but I guess not. So what am I really doing? I'm looping over 200,000 things. And for each thing in my loop, I'm iterating from j up to the square root. And then I'm doing just some simple math. Wow, how is this not fast enough? Python sucks. So, hey, just double check if there's something else going on. I just print the I am on. Yeah, I guess it's just very slow. Huh. How is it so slow? Maybe it makes some sense. I guess, like, it doesn't make that much sense to me. At each one of these steps, it's doing some computation proportionate to a square root of 200,000. What is that? $400? Doesn't seem like it should be so slow. Maybe I should like rewrite it really quickly in a different language. And something else I could do, it probably won't help at all, but I mean I can take this math.square root out of the inner loop. So I can be like, wait, can you write for loops like you do in other languages, like for int j equals 0, j less than, like you can write like a conventional for loop in Python, right? I'll just Google that. I don't think it should be that inefficient to call math.square root, but it's possible. And wow, okay, it just doesn't exist. Okay, but I can write a while statement. Okay, so j equals 1 while j times j is less than I. I'll say less than or equal to I. And j plus 1. I don't think this should matter very much. But I'm like, I guess in theory, the square root computation is probably a little more complicated than this squaring operation, which is doing the same thing. Okay, yeah, it doesn't seem like it makes any difference at all. Unsurprising. I can get rid of this now. So while j times j does not equal I, because this is equivalent to I over j not equaling j. And I can, well, I guess there's no reason to get rid of the j greater than 1 line. Let me just make sure I didn't destroy the correctness really quickly. Okay, looks like it's still correct. How much time do I have? Maybe I should rewrite in another language. 13 minutes. I guess that's enough time. It's sort of just very frustrating. I guess I should just stop doing contests in Python. Because yeah, 200,000 times, what was it, 400 should be easy peasy. Yeah. Maybe not. I guess it is actually objectively large. It's like a 2 million, 20 million. No, it's less than 100 million. It should really be fast enough. Yeah, maybe I'll try rewriting it in C. I wonder if I can get like the boilerplate from someone. C Codeforces boilerplate. Just copy this real quick. Today. Oh, wow, this is like sort of a complicated program. I don't really understand what's going on here at all. Okay, I guess this is like so they can write simple for loops without thinking about it. And I don't know. It's been so long since I ran C code. I don't really want to do it in the next 10 minutes. I don't really understand what this is at all. So cin is standard in. So we include like bits.standard in C using namespace standard. Oh, okay, so I guess this is the output of like some specific function. I want something less complicated than this. More intelligible. Does everyone have like super complicated templates? Maybe I need more complicated templates. My own repository for CP purposes. Very nice. Given n different values of coins. I don't know. Maybe I'll just admit defeat despite having this working algorithm that is... I don't know. I wonder if there's other ways to speed it up. I guess all we're keeping track of is like 2 numbers and 1 array, which we have pre-allocated. Yeah, I guess this is like while statement is what's taking up all the time, but I don't think one can do any better than this. Yeah, I might just stop here. I don't really feel like rewriting in the next 3 minutes. Okay, maybe I'll learn how to program in C and just switch to that, because it is sort of disheartening to like just not be able to do this problem. Yeah, I don't think there should be any ways to optimize. It's like very tight. Okay, well, 1300 is fine. Yeah. Oh. Okay. Yeah, I'm feeling kind of cooked. I guess that's it for today. I'll do some learning for next time. All right, thanks everyone for watching. I enjoyed doing the contest.